Welcome to ECE476 Advanced Embedded Systems, lecture number 14. In this lecture, we're going to look at the math library and the random library. Now, there are a bunch of different libraries in MicroPython. Here we're going to go over two of the libraries that are fairly commonly used, the math library and random library. If you want to get more detailed descriptions, here's really two really good links. It's the Python 3 organization talking about the math library and the random library. And as a note, MicroPython uses a subset of these libraries. The Raspberry Pi Pico doesn't have nearly as much memory as Raspberry Pi, so some of these have been truncated just to make space on the Raspberry Pi Pico. So some of the things we'll be doing this lecture, we'll look at the convolution routine. With convolution, I can find the product of two polynomials. For example, here, I've got two polynomials, multiply them together, and here's 90 plus 15x plus 96x squared, and so on. We'll look at increasing the random library to include different distributions. For example, here's a binomial distribution, a coin toss. If I toss a coin 10 times, here's how many heads I got. First trial, I got 5 heads, 6 heads, 4 heads. Or I can use the graphics display and show here's how many times I got 0 heads, 1 heads, 2 heads, 3, 4, 5. What the nice thing about that is if I increase the number of coin tosses to 1,000 times, I start to get a fairly well-behaved distribution. That's a PDF. We'll look at other distributions like exponential, Pascal, binomial, and finally, we'll look at how to use a normal distribution to simulate a candle flickering. So here, GP16 would be simulating a candle flicker. So that's where we're heading. So let's start out in the math library. To see what the contents are in the math library, I can do import math, then directory math, and it shows you all the different functions that are in the math library. A brief description of these follows. The math library includes some constants. Pi is the ratio of a circle's circumference to its radius. Tau is 2 times pi, the ratio of a circle's circumference to its diameter. E is a natural constant. E to the x is the only function equal to its derivative. It also shows up in many different places like calculations, interest rates, calculations, calculus, and so on. NaN is not a number. It's not equal to anything other than not a number. It serves as a placeholder. INF is infinity. A note on not a number. This is used in control systems fairly often. If you have a dynamic system in state space form, that's matrix form, I can represent it as x dot equals ax plus bu. So essentially x would be the energy in the system, like the voltages on the capacitors. The change in voltage is a function of the circuit, that's your A times X, and the input, B times U. Y is what you're looking at of the end voltages on the capacitors. How do they combine to produce the output plus the input? This is kind of cumbersome. I've got to keep track of 4 matrices for any given dynamic system. Well, using not a number, I can store these in one matrix. I'm going to separate the A, B, C, and D by not a numbers. That makes it easier on the subroutines to pull out where's the A, B, C, and D by looking for the knotted numbers. So that's kind of one use of it. It's a space holder. Yeah, and the net result is I'm just dealing with one matrix from now on rather than 4. The math library includes trig functions. You got sine, cosine, tangent, arcsine, arccosine, arctangent. Essentially, trig functions are all about the unit circle. If I have a circle with a radius of 1, pick a point on the circle, its x-coordinate is cosine of the angle, the y-coordinate is sine of the angle. Draw a tangent at 1, where it hits your line is the tangent of the angle. Arctangent is going backwards. If I know the tangent is 3, what is the angle? Arctan 2 is arctangent for 360 degrees. Essentially, that keeps track of which quadrant you're in. The sines and cosines can also be defined by the complex exponential. So cosine of x is e to the jx plus e to the minus jx over 2. And sine of x is e to the jx minus e to the minus jx over 2j, if you care. Now, trig functions take some time to execute. You can determine how long it takes to find a cosine function by using the tick microsecond. And here what I'm going to do is I'm going to find 1,000 cosine functions. So anyway, here's x. Here's the cosine of x. I want to measure how long this takes to execute. So what I'll do is I'll record the time before I go into this loop, record the time when I'm done. The difference in time is how long it took to do everything. That's count to 1,000, do a multiply, do a cosine. Well, if I take out the cosine function, just comment that out, this took 14 milliseconds. If I put that back in, it took 59 milliseconds, meaning the difference in time, 45 milliseconds, is how long it took to do the cosine function. Well, that's for 1,000 cosines, so each cosine is roughly 45 microseconds. Give you an idea of how expensive sines and cosines are. Really not too bad on a Pi Pico. Hyperbolic functions. The math library also includes hyperbolics. Now, one way to think about this is the cosine of jx is hyperbolic cosine of x. The sine of jx is, I think, j times the sine of jx. So basically, it's replace x with a complex number, and you get the hyperbolics. Hyperbolic cosine is also the shape of soap films and hanging wires. So if you drive out to the countryside and you see the transmission lines, this shape right here, that's a hyperbolic cosine, if you care. This is also something that you can derive when you take calculus of variations. That's a course that comes after Calc 1, Calc 2, Calc 3 differential equations. I think 2 courses after that is calculus of variations. So it's fairly high-level math, but you can prove that. In the math library, there are statistics functions. You can find the factorial of a number. The factorial of 4 is 4 times 3 times 2 times 1. The gamma function is the same as factorial, but it works for non-integers as well as integers. And the error function is the integral of e to the minus x squared. Basically, it looks like this, going from minus infinity to plus infinity. It goes from minus 1 to plus 1. I can convert the error function to the area to the left of a number on a normal distribution. That's called the z-score. So I want to find out what is this area for standard normal distribution, mean of 0, standard deviation 1, something we'll get to a little bit later. That's the error function. I need to take the error function of z divided by square root of 2. Need a parentheses. Add 1 to it. That brings it up to 0 to 1. Divide by 2. So that'll be the area to the left, this guy right here. In the math library, there are exponentials. exp of x is e to the x. expm1x is e to the x minus 1. When I have a different power other than e, I just use the star star. That's standard Python syntax. So 2 star star x is 2 to the x. The log of x is log base e. Log 2 is log base 2. Log 10 is log base 10. We can also round, but do ceiling, let's take the number 2.3 and round up. Floor is round down. There's also square root of x. I can also take it to a power like x to the 0.7 would be like the 0.7th root of x. That's the math library. The random library we're going to spend a little bit more time on. The random library includes functions, includes different distributions, how to generate random numbers, something we're going to use quite a bit. It's kind of a fun way to do things like roll dice, draw cards. In the random library, there's a couple functions. I can find them by importing random and then doing a directory. Again, this is a subset of what's available on Python 3. The functions that are available in MicroPython our random integer. That'll give me a random integer in the range of a to b. Random is a random number between 0 and 1. Rand range of start, stop, and step will be able to want to go from 1 to 3 steps of 0.5. Rand range of stop, say rand range of 6, it'll give a number between 0 and 6. Seed initializes the random number. If you don't do a seed, it'll use the system clock, system time. And uniform returns a uniform distribution in the range of a to b. So, let's kind of use a bunch of that stuff. Before we do that, I want to include the convolution, come up with a convolution routine. The reason being is convolution is really useful in probability density functions. It also multiplies polynomials. So for example, suppose I want to multiply these three polynomials together. What I could do is multiply by hand or convolve. This is the convolution of a and b. Take that result, convolve it with c. I get the product of the three polynomials. So to do that, I need a subroutine that does convolution. That'd be this guy. This one we looked at before. I am going to take a of k times b of n minus k, basically take the two polynomials, flip one, then slide them over, taking the product. Clipping, so if I'm out of range, I don't have problems with the arrays out of range. If I want to take this previous example, what is a times b times c? I can say, here's polynomial a, that means 3 plus 2x plus 1x squared. B is 5 plus 2x squared, and here's c. Convolve a and b, take that result, convolve it with c, and here's what you get. So what that means is the product of a times b times c is 90 plus 15x plus 96x squared plus 136x cubed, and so on. So that's one use of convolution. It is a much easier way to multiply polynomials. I shouldn't say easier, because when you multiply polynomials, you're really doing convolution. With a convolution function, I can find the product a whole lot easier than I can do it by hand. So, let's get into some random probability functions. Now, in statistics, we use combinations and permutations fairly often. A combination is, I'm going to do something like if we've got 20 people standing in line, I'm going to pick out 6 for a volleyball team. If the order doesn't matter, that'd be 20, pick 6. How many different ways can I pick 6 people from a group of 20? That's n choose m, 20 choose 6. That's equal to n factorial, 20 factorial over 6 factorial times 14 factorial, the difference. There's also permutations. Permutations is if order does matter. So for example, I'm going to take the first one, that's the setter. The second one is the strong side hitter. Third one is the middle hitter. Fourth one is the right side hitter, and so on. If order matters, that's a permutation. The number of ways of drawing n items, m items from a population of n, so like 6 players from a population of 20, would be 20 pick 6. N factorial over n minus m factorial. Now these don't exist in MicroPython, but I can write those routines fairly easily. I'll just define n choose m as the integer of this ratio permutations would just be the ratio. And to see what that does, let's go to, in Python, n choose m of 20, 6 is not a valid function. If I run this, that loads it into memory. And now I can say, what is n choose m, 20 people choose 6. There's 38,000 different ways I can pick 6 players for a volleyball team from a population of 20. That's if order doesn't matter. If order does matter, and pm of 20, 6. That is a big number, 27 million something. That's combinations, permutations. Again, fairly useful functions. If you write those, define them, low to memory, you now have access to permutations. Next, before we get into the probability density functions, let's kind of back up a little bit, talk about probability density functions. There's a PDF and a CDF. The PDF is the probability that y equals x. So for example, if I roll a four-sided die, there's a 1 in 4 chance of getting a 1, 2, 3, and 4, no chance of getting a 5, no chance of getting a 6. That's the PDF. The CDF is the integral of it. What's the probability that x is less than a number? So we can say the probability that x is less than 2.5 is 0.5. That's this number right here. That's the integral of the PDF. Now I can have discrete PDFs and continuous PDFs. A discrete PDF, I have to have only discrete values. Like an example would be rolling a four-sided die. The answer has to be integers. I can also have continuous PDFs. Like I'm going to have a number between 1 and 4. Could take on any number like 2.7832. The integral of the PDF is the CDF. Here the CDF is kind of useful because if I want to pick a number, I take a probability, number between 0 and 1, say 0.7, come over to here, and that's the corresponding x. Same thing on the discrete probability, pick a number like 0.7, that gives you the number 3. Also kind of definition, the mean and standard deviation. The mean is the average. The definition is the sum of the value times its probability. So like for a four-sided die, the average is 2.5. The variance is the average square distance to the mean. So this number right here, there it is, the numbers we can get are 1, 2, 3, 4. The first one is 1.5 squared, 0.5 squared, 0.5 squared, 1.5 squared. Add them all up, that's the variance. The square root of the variance is the standard deviation. The standard deviation is a measure of spread. So just some kind of definitions. Now let's get into some different probability density functions. Now these are things that aren't in the random library, but occasionally run into these probability density functions. With a little bit of coding, I can create them. So for example, let's do a Bernoulli trial. A Bernoulli trial is a coin toss. I either get a 1 or a 0. So for example, I could toss a coin. If it's a fair coin, half the time I get a heads, half the time I get a tails. I could roll a six-sided die. If I get a 1, that's a success, probability of 1/6. A 0 is a failure, probability of 5/6. If I go to Vegas, I could bet on red in roulette. That's probability of 15/31. I could bet on 10 black in roulette. Probability 1 in 31. So the PDF for a Bernoulli trial only has two outcomes, success or failure. This is P. This is 1 minus P. In statistics, all probabilities add to 1. So these two areas have to be 1. If I flip the die, roll or flip a coin, something happens. In Python, I can do Bernoulli trials with the rand function. For example, suppose the probability of success is 0.7. I can flip a coin 5 times with a probability of 0.7, and if the random number is less than 0.7, that was a success. Otherwise, it was a failure. If I run that, here we got 3 successes out of 5. To illustrate that, here I'm going to toss a coin 10 times. Probability of a heads is 0.5. If I succeed, I'll get a win, otherwise I get a loss. If I run that, I can see over here in the shell window the trial number and successes. I can also put that in the graphics window. If I do a bar chart, I can show you here's how many successes and failures I got. That's probability of 0.5. If I change the probability, let's make the probability 0.1. So I got 2 successes. I can see that in the bar chart. A binomial distribution is n Bernoulli trials. So instead of just tossing a coin once or rolling a die once, I'm going to roll it n times. So for an example would be flip a coin 10 times and count the number of heads. Roll a 6-sided die 10 times and count the number of ones. The PDF for binomial distribution is n choose m, p to the m, 1 minus p to the n minus m. And for details on this, you can check out 341 Random Processes or book on statistics. Here we'll just take it as granted. That's the probability of getting like 3 ones rolling 10 dice. Well, for example, I can calculate the odds. If I roll 10 dice, probability of success is 1/6. Probability of getting 3 ones would be 10 choose 3 times 1/6 cubed times 5/6 to the 7th. 15% chance of getting 3 ones on 10 6-sided dice. If I do that for all numbers, that's what the PDF looks like. In Pascal, I can do that, or Python. What a binomial distribution looks like would be as follows. In Python, I can define a subroutine called binomial. What I'm going to do is I'm going to flip a coin n times. Probability of success is p, so count the number of successes in n coin tosses. With that, I can do a Monte Carlo simulation. Monte Carlo just means I run the experiment n times. So let's toss a coin 10 times, determine how many heads I get, and this is a fair coin toss, probability of heads is 0.5, and print the result. If I do that, this is the trial number, and I got 4 heads, 5 heads, 6 heads, 2 heads, 8 heads. If I put that on a bar chart, that's what it looks like. With Monte Carlo, if you don't know the PDF, what I can do is just run the experiment a bunch of times, like 1,000 times. So there's 1,000 runs. Oops. Had to make this dimension 11 to catch all elements. Plot them out, and that's basically the PDF. So knowing very little about random processes with the Monte Carlo run, I can basically tell you what the PDF looks like just by running a whole bunch of experiments. It also makes kind of a nice graphics display on our board. So that is a, where are we? Binomial distribution. In Python, again, like I said, you just do a Bernoulli trial n times. And I can try other things. So this is for a coin toss, probability of heads is 0.5. Suppose let's do 1/6. It's going to roll a 6-sided die 10 times, count the number of ones. If I just do that 10 times, here's the number of successes I got in 10 rolls in the bar chart. Repeat 1,000 times. And here's all the data. Plot them on a bar chart. And kind of note, this is where graphs are kind of nice. This is the bar chart, number 0s, 1s, 2s, and 3s. This is much easier to understand than 1,000 numbers. Same information, but I don't really need to include both in a report. This is why we like graphs in engineering. A whole lot easier displaying this than 1,000 numbers. Where are we at? There we are. So that's a binomial distribution. Let's look at a uniform distribution. A uniform distribution would be like roll a 6-sided die. I can get the numbers 1 through 6. There's a couple ways of doing that. I can do rand range. That gives me numbers 0 through 5. Plus 1 gives me the numbers 1 through 6. I could do rand range of 1, 7, 1. This goes from 1 to 7, steps of 1. And again, in Python, I don't get to the last endpoint. It's quit if you're equal to. Or I can say, here's the die rolls, 1 through 6. Pick one from that. That's what the choice function does. Pick one from that population. The PDF looks like this. Equal probability for all numbers. With that, I can start having some fun. For example, in Dungeons & Dragons, there's different spells you can cast. If I cast an insect swarm spell, the damage I do is 4 10-sided dice. An ice storm is 2 8-sided dice plus 4 6-sided dice. Well, I can do that in Python. Let's create a function called dice. I'm going to toss n dice of so many sides, like 4 10-sided dice, 3 6-sided dice. I'm going to start counting. For n dice, pick a number in that range, add them all up, return x. Then insect swarm would be 4 10-sided dice. An ice storm are 2 8-sided dice and 4 6-sided dice. I can show you what that looks like. So for example, let's do the insect swarm. Adding up 4 10-sided dice, I can come up with a subroutine in Python. I'm going to roll n dice of so many sides. So an insect swarm is 4 10-sided dice. When I run that, it's going to cast 10 insect swarms. Here's the spell casting, how much damage it did. Or keep track of how many times I got 1 damage, 2 damage, 3 damage. There's the damage versus number. And that doesn't look like much. That's with rolling 10 insect swarms. Do that 1,000 times. That's a Monte Carlo run. Here's the results for all 1,000 runs and what it looks like. It's starting to look like a nice bell-shaped curve. That's with 1,000 rolls. Increase the number of rolls to get smoother. If I want to do a different spell, like Ice Storm, that would be 2 8-sided dice plus 4 6-sided dice. That is Ice Storm. If I do that, cast 10 Ice Storm spells. Here's how much damage I did, and a bar chart. Cast 1,000 Ice Storm spells. That's the damage versus frequency. So that's the uniform distribution. Kind of useful in rolling dice. There's an exponential distribution. An exponential distribution would be a run a Bernoulli trial until you get 1 success. For example, that'd be the number of coin tosses until I get a heads, number of times I roll a die until I get a 1, number of days you do the dishes until somebody notices, number of days until your car doesn't start. The PDF is p times 1 minus p to the n minus 1. And here's what it looks like. In Python, I can do that. There's kind of 2 different ways. Literally what I would do is I'm going to keep counting until I get a number bigger than p. So like if p is 0.5, keep flipping a coin until the random number is bigger than 0.5. If p is 1/6, keep going as long as p is bigger than 1/6. As soon as it's less than 1/6, I kick out. So this would be like roll a 6-sided die until I get a 1. If I do that, here's the number of times. This is the trial number, and here it is. The first trial, it took 18 rolls to get a 1, 14 rolls, 4 rolls, 2 rolls, 5 rolls. That's one way, kind of inefficient. The problem with this approach is when p is small, I'm stuck in this loop a long time. A more efficient way is to use the CDF. The CDF kind of looks like this. If I know the probability, 0 to 1, I can calculate this number. And the calculation would be rounding up of minus the log of 1 minus y, that's the probability, divided by p. The nice thing about this is I don't have to iterate, I just calculate it. The problem is it's not as obvious what you're doing, but both answers are equivalent. In Python, I can do that. So let's do an exponential distribution. I'm doing the latter method. It's more efficient. I am going to flip a coin until I get a heads. If I run it 10 times, there's the number of heads. This actually goes out to infinity. I'm just going to clip it at 40 so I don't go out of bounds for my matrix. If I run this 1,000 times, that's Monte Carlo, I can kind of see what the PDF looks like. Nice decaying exponential. That's the probability of 0.5. If I make the probability 1/6, that'd be like a 6-sided die. Roll until I get a 1 on a 6-sided die. Now what it looks like, kind of spread out. If I roll until I get a 1 on a 20-sided die, well, it kind of comes a little bit slower. And this is a big number just because if it's out of bounds beyond 40, I just clip it at 40. So that's an exponential. And here's the number of rolls it took to get that many success until I got a success. Pascal distribution. A Pascal distribution is you run a Bernoulli trial until you get R successes. This is an exponential distribution. Exponential distribution until you get R successes. So that'd be like the number of coin tosses until you get 3 heads, number of times I roll a 6-sided die until I get 3 1s, number of days until 3 people notice that you did the dishes, and so on. The PDF, this is how you calculate the probability of so many rolls. I can also do that in Python. So what this would be, I've got an exponential distribution. I am going to count R exponentials. So if I want to have 3 successes, probability of success is 1/6. First time I tried it, took 12 rolls to get 3 1s, 20 rolls to get 3 1s, 9 rolls to get 3 1s. Or if I have probability 0.5, I want to get 3 1s, 3 successes and coin tosses. Here's how many rolls it took to get 3 successes, with probability of success being 0.5. That'd be like a coin toss. If it is 1/6, how many rolls it took to get 3 1s on a 6-sided die. Again, if I increase that to 1,000, I can see the PDF a little bit easier. That's Monte Carlo. As the sample size goes to infinity, I approach the PDF. Kind of looks like this. So that's some of the discrete distributions you can use. There are also continuous distributions. For example, a uniform distribution has the same probability over a range. So like this would be a uniform distribution with numbers between 1 and 4. An example of that would be like a resistor. We say resistors have a 5% tolerance. So here's your nominal resistance, say 1,000 ohms. It's somewhere between -5% and +5%. We normally assume a uniform distribution for lack of anything better to assume. Can assume any value between 95% and 105%. To generate a uniform distribution in Python, I can just use the random function. Random returns a number between 0 and 1. Uniform generates a number between A and B. So this is a number between 5 and 6. There are exponential distributions. This would be like the time until an event happens, assuming the event has fixed probability over a small range. For example, the duration of a telephone call is an exponential distribution. The time until one atom decays. The time until a customer arrives at a store. Those are all things that have an exponential distribution. So the PDF is exponential. The CDF is the integral of it, the area to the left. The CDF is actually more useful. So to generate a random variable, what I do is pick a number between 0 and 1, come over to the CDF, and that's your variable. In Python, what I do is I use the CDF, and I guess the number between 0 and 1. The time is the log minus the log of 1 minus y over p. So I could try that if p is 1/6. calling that function, I can generate a distribution y that has an exponential distribution with a probability of 1/6. So doing it 5 times, it was 10.11 seconds, 14.17 seconds, 0.81. These have exponential distributions. And the mean is 1/p. Gamma distribution is the time until k event happens. So that'd be same as an exponential distribution, but instead of 1 phone call, I want to have 3 phone calls, or 3 atoms decay, or 3 customers arrive. This is the PDF, which looks like that. In Python, I can just do k, or 3 exponentials. So this would be 3 gamma distributions with the probability of 1/6 and 3 events. Total is 19 seconds until 3 customers arrive, 14.8 seconds until 3 customers arrive, and so on. That is a gamma distribution. And finally, a normal distribution. This is the distribution you're probably very, very familiar with. Probably the most important distribution in all statistics. It's the standard bell-shaped curve that you've seen over and over again. A normal distribution is defined by 2 parameters, the mean, that's the average, and the standard deviation, that's the spread. If the standard deviation is 0, that's just a line. As the bigger the standard deviation is, the bigger the spread is on the data. The PDF has this equation. And part of the reason the normal distribution is so important is the central limit theorem that says if you add distributions under very general assumptions, you get a normal distribution. And we've seen that over and over again. When I roll dice, I get this shape. I flip coins, I get that shape. An example, if I sum 12 normal distributions, if I sum 12 uniform distributions between 0 and 1, subtract 6, that gives me the red line. A normal distribution with a mean of 0, standard deviation 1, same mean, same standard deviation, is the blue line. Basically, they're identical. That's the central limit theorem. The z-score is the area of the tail. That's actually used quite a bit in statistics. If I want to find out what's the probability of doing so much damage, I find out how far is that number from the mean in terms of standard deviations. That's your z-score. Find the area of the tail. To do that, I calculate the z-score. For example, if the mean is 10, standard deviation is 5, what is the area to the left of 3? So here's 10, standard deviation is 5, here's number 3. What is this area? To determine that, I find the z-score. How far is 3 from the mean in terms of standard deviations? Find the area to the left. That's the area function of minus z, well, negative would be this tail, over square root of 2 plus 1 over 2. And the area of the tail, the z-score is 1.4. The area under the tail is 0.08. So the area to the left of minus 1.4 is 8%. To generate uniform or normally distributed variables, Python doesn't have a rand-n function like MATLAB does. But what I can do is a uniform distribution between 0 and 1 has a mean of 1/2 and a variance of 1/12. A property of distributions, when you add them together, the means add and the variance adds. Add 12 uniform distributions, the variance becomes 1. The mean is 6, so subtract 6, and I get a mean of 0, variance of 1. So that looks like a normal distribution with a mean of 0, standard deviation of 1. Using that trick, I can create my own function in Python. This is your random function, returns a normally distributed variable with the mean of 0, standard deviation 1, or standard normal variable. When I call it 5 times, these are the numbers I get. Again, it goes from minus infinity to plus infinity, standard normal curve in theory. This actually goes from minus 6 to plus 6. Set it at 0. What I can do with that is I can create a candle flicker. So I'm going to pick a normally distributed variable. That'll set the duty cycle. Normally it's 50%. The standard deviation is 10,000 on duty cycle. Display that for 50 milliseconds and keep on displaying it. What that looks like, going over to Python, here's the candle flicker. Run that puppy. And what it looks like is 16. Looks like a flickering candle. That's one thing you can do with a normal distribution. With that, I can build an electronic candle. If I blow on it, it goes out. If I let it match to it, have an infrared heat sensor, the light turns on and it flickers. So that's some of the things you can do with the math and random libraries. In the math library, you've got trig functions, exponentials, constants. In the random library, you can generate random numbers. With a little bit of coding, I can also implement exponential, gamma, Poisson, normal, and other distributions. That's lecture number 14 for ECE476, Advanced Embedded Systems.